Okay, I think this is the sixth video for chapter 11, and I'm going to introduce now the second theory. If you remember, the name of the chapter is Theories in bonding theories, or covalent bonding theories, I guess. And so this chapter contains two theories. The prominent one is the first one we discussed. The VB theory, valence bond theory, is the most common, and it's I suspect you'll be tested quite a bit on this. And in fact, it's one of the things that and, when we're doing our Lewis structures and we're getting our shapes and we're talking about polarity and we're writing all this stuff, one of the common things that people will say when you're analyzing a compound is we'll basically say, okay, here's the Lewis structure. The bonding type around this carbon is using sp2 hybridization, and so it's a very common thing to kind of mention, and you'll see that. The second theory is not as widely used, and it has certain advantages and certain drawbacks. So it's known as molecular orbital theory. And the way this theory works, the way MO theory works, what its premise is it basically says when atoms bond together, the orbitals a way of looking at the bond is that new orbitals are formed that reflect the combined atoms. Okay. Now in VB theory, that wasn't what we did. In VB theory, we took an atom and we hybridized its orbitals, its atom's orbitals, and then we used that in conjunction with another atom's orbitals to form either an end-to-end sigma bond or a side-by-side pi bond. MO theory is different. It essentially says the orbitals, basically the mathematical way that you define where is the electron, is actually different for a molecule, and that way that the math we use is known as a molecular orbital. So it kind of takes the two electrons together that form a bond, two or more electrons that form a bond, and they basically come up with math that describes that orbital. So again, it's another math technique grounded in the quantum mechanics, but it essentially describes the nature of the electron's location in that bond. Okay. Now, I'm going to kind of so here I'm going to gloss over a few of the things in this chapter. I recommend that you read the chapter, but some of the stuff is a little confusing. And this is the nature of molecular orbital theory. It is actually a much more advanced theory, and you'll see that once you get past just molecules that have just two atoms, once you add in a third atom, the math gets so complicated that the theory kind of breaks down. Or becomes more cumbersome, I think, than the other theories. But it is interesting, and it does actually predict certain things that we see in chemistry that are unique. So let me start with the simplest bond here, and that is a bond between two hydrogen atoms. So again, H2 gas is formed when two hydrogen atoms and their electrons come together, that we've seen, and they form a nice little bond like this. All right, so let's take a look at what molecular orbital theory says. Well, what molecular orbital theory says, and I'm just going to call it MO theory, says, is that each of these H's brings to the party its own orbital. So this H has an orbital. It's a 1s orbital, and so does this H. It has a 1s orbital also. Okay. That's looking at them separate as separate atoms. MO theory says when you're talking about these two atoms combining, they're going to form now molecular orbitals, and the number of molecular orbitals will be the same number as the number of orbitals when they were apart. So when we think about bonding hydrogen, essentially what we're talking about is there being two orbitals, two molecular orbitals that are in existence as hydrogen is bonded together. The one orbital is known as the 1s sigma, and the other is known as the 1s sigma star. Now, this is all math. This all falls out of the math, and what it's essentially saying is that this orbital they call the bonding orbital, and this orbital they call the anti-bonding orbital. And it's just another way of saying that what we've added here is we've essentially combined two waves. Again, molecular, an orbital is really just a wave mathematical description. We've combined two waves, and we've combined them either where the waves are additive, they add together, or when they're destructive, meaning they subtract from one another. So the bonding orbital is when they're added, and the anti-bonding is when they're subtracted. It's just math. Don't even try to make any kind of reality out of it because it's difficult. But here's now how the rest of the theory goes. The rest of the theory goes, all right, so you combine the orbitals, the atomic orbitals together into the molecular orbitals, and then you fill them in the way we've always filled orbitals, which is one electron at a time. So we have each hydrogen is bringing one electron to the party, and the first one gets filled here, and this next one gets filled here, and you're done. You only have 2 electrons in hydrogen. And so essentially the molecular orbitals for the diatomic hydrogen molecule are filled like this. All right, what's the point? Here's now the big point. We now can make a statement upon the strength of this bond, or for that matter, even the existence of this bond, by doing just a little bit of math. And here's what the math goes. The math says is, take the number of electrons that exist in bonding orbitals, in this case 2, subtract off the number of electrons that exist in anti-bonding orbitals, in this case 0, divide that result by 2, and what you end up with is a description of what we call the bond order, meaning how strong is this bond, or for that matter, does it exist at all? And when we do our little math here, we say 2 minus 0 divided by 2 equals 1. This is now a bond order of molecular orbital theory says that diatomic hydrogen has a bond order of 1, meaning it forms a single bond. Okay, so let me do another example, and you'll see where this looks like it's relevant at all. Because at this point it sounds like, okay, so what? So what? Let me do the second example. Second example, instead of it being hydrogen, it's going to be helium. Again, each helium atom brings to the party 2 electrons. Okay. So let's actually take a look at what He2 looks like, the diatomic helium. Again, we would draw this somehow in a Lewis dot structure. I won't waste a lot of time on that at the moment. You'll see why. But let's actually use the same theory that we did before with hydrogen. We'll do it with helium. So each helium has 2 electrons that it brings. And so let's fill them. So it goes 1, 2, 3, 4. That's all we have is 4 electrons. Now let's take a look at the result. Well, the result is that the bonding orbital is filled and the anti-bonding orbital is filled. So let's calculate the bond order. Well, the bond order is the number of electrons in bonding orbitals, 2, minus the number of electrons in anti-bonding orbitals, 2. Divide that result by 2, and what do you get? You get a big fat 0, meaning that the bond order between the 2 helium atoms is 0, meaning it does not form a bond. This theory says that diatomic helium is impossible, and sure enough, it's never been observed. So this theory allows the prediction of the fact that diatomic helium does not exist, where the other theory, V-separate theory, didn't have a similar observation. Okay. Right. Now, to take this just a little bit further, and the book kind of does this as well. Let's see, do I have time for it? No. I'll do one last video on the last bit of comments on MO theory, and then that'll be it for Chapter 11.